Hey everyone, and welcome. Today we are diving right into the heart of every digital device you own. We're going to crack the code, so to speak, on how computers actually count, think, and process the world around them.
Have you ever really stopped to think about it? Deep down, a computer is basically just a giant collection of switches, and each of those switches can only ever be on or off. That's it, a high voltage or a low voltage. So the big question is,
how on earth does that super simple two-state system manage to represent everything? From your favorite song to a 4K movie to a massive financial spreadsheet? Well, the answer lies in a completely different way of counting.
To really get a handle on that different way of counting, we've got to start with what we know, our world. We think, breathe, and live in what's called the decimal system. Our system is called base 10 for a pretty obvious reason, right? We use 10 unique digits, 0 through 9. And it's a positional system, which just means a digit's value depends on where it is. You've got the ones place, the tens place, the hundreds, all based on powers of 10. It feels totally natural, probably because we happen to have 10 fingers.
But here's the thing. Computers don't have fingers. They have circuits, and that means they need a whole different language.
And this slide just lays out that contrast perfectly. We think in nuance, using our 10 digits to express basically any number we can dream up. A computer, though, operates with this beautiful, brutal simplicity. A circuit is either on, which it calls a 1, or it's off, which it calls a 0. That's the whole game. Welcome to the base 2 world.
So this is the binary system. And you've got to understand, this is the native tongue for every single digital machine on this planet. Every photo, every email, every single calculation gets broken down into a long string of these ones and zeros.
Now, here's the crucial thing. While computers only speak binary, reading those massive strings of ones and zeros is a total nightmare for us humans. So we came up with some clever shorthands. Think of this chart as our roadmap. We've got our decimal, the computer's binary, and then these two others, octal, which is base 8, and hexadecimal, base 16. They're just compact, much more friendly ways for us to write down binary code.
Okay, so how do we actually translate a number from our world into one of these other systems? You might think it's complicated, but the good news is there's one simple, elegant method that works for all of them. It's called the division method. All you do is take your decimal number and just keep dividing it by the base you want. So you divide by 2 for binary, 8 for octal, or 16 for hexadecimal. Each time you divide, you write down the remainder. And then, this is the key part, you read those remainders from the bottom to the top to get your final answer. Let's see it in action. Here we are converting the number 12,345 into binary. We just divide by 2 again and again and write down the remainder. It's always going to be a 1 or a 0. Once we hit 0, we stop. Then we read that column of remainders from the bottom up. That last remainder is what we call the most significant bit, and the very first one we got is the least significant bit. Put them together, and there's our binary number.
Now, what about octal? We'll take the exact same number, 12,345. The rule doesn't change one bit. We just divide by the new base, which is 8 this time. The process is exactly the same. Keep dividing, record the remainders, read them from the bottom up. Easy.
and the same logic works perfectly for hexadecimal. We divide by 16. Now there is one little twist here. Since it's base 16, your remainder can be bigger than 9. When that happens, we just use letters. So a remainder of 10 becomes A, 11 is B, all the way up to 15, which is F.
Great. So we can translate our numbers for the computer. But what about going the other way? How do we read what the computer sends back? How do we decode its native binary language? To get from binary back to our good old decimal system, we use something called positional weights. Starting from the right, every single position represents a power of 2. So you multiply each digit, the 1 or the 0, by whatever its position is worth, and then you just add all those numbers up. It's a really direct way to translate the machine's language back into our own. But as you can probably tell, binary numbers get really long really fast. I mean, trying to read or type that out is just asking for a mistake. And this, right here, is exactly why we need those handy shorthands we talked about earlier.
And here is the brilliant shortcut. To turn a long binary number into octal, you just group the digits into little sets of 3, always starting from the right. Then you just convert each of those tiny 3-bit groups into a single octal digit. It's really that simple.
And for hexadecimal, it's the exact same idea, but maybe even more powerful. This time, you group the binary digits into sets of 4.
Each group of 4 bits corresponds perfectly to one of the 16 hexadecimal characters. This is why you see hex all over the place in programming. It is an incredibly neat and tidy way to write down binary data.
Okay, this is where it all clicks together. Once you understand these grouping tricks, you start to see binary as this kind of universal translator, a bridge that connects all the other systems.
So, what if you need to go from octal to hexadecimal? You don't need some new, complicated rule. You just take the easy path through the middle. First, you turn each octal digit into its 3-bit binary version. Then you take that new long binary string and you just regroup it into sets of 4. Convert those new groups to hex and you're done. You see, binary is the bridge.
And that is the absolute most important thing to take away from all of this. Decimal, binary, octal, hexadecimal. Yeah, they look different, but they are not different things. They're just different notations, different ways of writing the exact same number.
So, we've learned how to translate numbers back and forth between our world and the computers. You could say we're officially bilingual now, fluent in the language of machines.
And now that we're fluent, it's time to put that language to work. In our next explainer, we're going to see how computers actually perform calculations using only ones and zeros. We'll get into key concepts like one's complement and two's complement and see how simple binary math is the engine behind all complex computing. Thanks for joining me.